Okay, here we go with CCEA Physics Unit 2, June 2016, and question 1 is about waves. Question 1. One kind of earthquake wave is called an L wave. In L waves, the particles of the material vibrate perpendicular to the direction of propagation. A particular L wave has a frequency of 0.002 Hz and a wavelength of 2500 kilometers. Which one of the following statements about L waves is true? Tick the appropriate box. L waves are transverse, L waves are longitudinal, L waves are neither transverse nor longitudinal. Well, the important information here comes in the form of this phrase here, vibrate perpendicular. And that's the definition of a transverse wave, where the vibration is perpendicular to the direction of propagation. And that means that L waves are transverse. Part 2. Explain what is meant by a frequency of 0.002 Hz. Remember, frequency is defined as the number of complete waves passing a fixed point per second. So a frequency of 0.002 Hz means that 0.002 complete waves are passing a fixed point per second. Use the information above to calculate the speed of this L wave and give your answer in meters per second. Well, we're given two bits of information. Above we're given a frequency and a wavelength. So we're told both of these. So frequency 0.002, wavelength of 2500 kilometers. And we really need that wavelength in meters. And we know that V equals F lambda. And putting that through the calculator, we get 5,000 meters per second. Part B. Ultrasound can be used to measure the diameter of the head of a baby in the womb. When ultrasound reaches the baby's head at A, some ultrasound is reflected back to the detector and produces pulse A on the CRO. Some ultrasound passes through the head to point B and is reflected back to the detector. This reflection produces pulse B on the CRO. What is the name given to the reflection of a sound wave? Well, we call those echo. The CRO is adjusted so that each horizontal division on the diagram above corresponds to a time of 40 microseconds. How long is the time interval between the arrival of pulse A and the arrival of pulse B at the detector? Give your answer in microseconds. So we've got 40 microseconds per square here, and we've got 1, 2, 3 squares. So that's 3 times 40 microseconds. And that gives us 120 microseconds. How long does it take for the ultrasound to travel from one side of the baby's head to the other? And give your answer in microseconds. You're advised to show clearly how you get your answer. Well, remember that when pulse A returns, pulse B has to travel on across the baby's head and then back. So the time for it is like a there and back travel. So the waves travel on, then they reflect, and they come back. So that extra time, that 120 microseconds, corresponds to a there and back journey. So going across just from one side to the other is going to be half of that. So you've got your 120, and then you divide that by 2 to get 60 microseconds. Part 4. Use your answer to Part 3 to calculate the width of the baby's head from A to B. Give your answer in centimetres. and a microsecond is 10 to the minus 6 of a second, in case you're wondering. So we use this fact that there's a speed of 1500 meters per second as it goes through the baby's head, and we have a time so distance is speed times time, and that's our 1500 times our 60 microseconds, which is 60 times 10 to the minus 6. Remember, we were told micros are 10 to the minus 6. We just put that through the calculator, and that comes to 0.09 of a meter, which is going to be 9 centimeters. Part 5. Explain why it is better to use ultrasound rather than X-rays when monitoring the development of a baby in the womb. Well, this is going to be a safety factor. So we know that X-rays can damage cells and cause cancers and stuff like that, so ultrasound would be much safer because it doesn't do that. Diagram below shows 4 of the 7 members of the electromagnetic spectrum. They are not arranged in any particular order. We've got infrared, ultraviolet, gamma and radio. Identify the 3 missing members of the electromagnetic spectrum by writing their names in the appropriate part of the table below. Best way to do this would be to put the spectrum in an order and then highlight which ones are missing. So this is them in order, and we are missing microwave and visible and X-ray. Gamma, UV, IR and radio are all included. So the bigger wavelengths are going to be at this end, this is where we're going to find the bigger lambda values. So the biggest lambda values here, so that's going to be microwave. This one here is going to be the biggest, and then the middle one will be visible and the bottom one will be X-ray. It's just about setting out the order of them and then deciding for yourself where each one belongs in terms of the size of those wavelengths.